Brad Chen is been here about a year and 3 years now, okay, and had previously, gee, time flies. I guess I wasn't here when you joined, so Brad had most recently been at Intel, a director there, doing work in performance technologies and the like, and performance management and measurement technologies. Was a professor at Harvard prior to that. Did his PhD at CMU and undergraduate degrees and masters at Stanford, right?
That's right.
So Brad, take it away.
Thank you, Alfred.
Okay.
This morning, I'd like to tell you a little bit about a different area than maybe you're used to hearing at Google. I spent the first couple of years at Google working on system infrastructure, looking at data center systems and studying performance. And when I looked at those systems, sometimes I felt like I was looking at something kind of like this. Wow, huge, massive, incredibly solid. You know, maybe I could find some polishing to do, but a lot of the time it was really hard to figure out how to really, change the world. About a year ago, I actually made a change to work on the desktop systems. I'm talking about, in the general area of the Chrome web browser. So this is still in the engineering group. And what I feel like when I look at the state of the art in the desktop is something more kind of like this. Now, this metaphor is a little bit exaggerated, but I am trying to make a point. Let me tell you a little bit more substance of behind what I'm seeing here. For example, privacy. The desktop systems we work with today sometimes seem to have paper-thin walls. Sometimes the walls are actually non-existent. And for many users, it's incredibly difficult to figure out what happens with their data and who they're actually sharing with. Safety. Your system was probably vulnerable the day you started using it. And the defenses that we create are not keeping pace with the threats that are emerging. Hygiene. The systems we work with are so complex, the APIs are so intricate that they're practically impossible to clean. And as a consequence of all of this, I don't think we deliberately built systems that were, had these kinds of problems, but the fact is that they were created in a different time, and times have changed. And so as a consequence, ownership of personal computers is commonly violated by things like bots and spam and viruses. And theft of information is also very common. These are huge problems that I don't really feel like we've dealt with, and that's sort of what I want to think about as we move into some of the work that we've actually been working on in the client area. So the next thing I want to tell you a little bit about is at more of a technical level, what has changed in desktop systems that actually, I think there's some really substantial changes that as a community we haven't actually done a very good job of recognizing. Then I'm going to tell you a fair amount of detail about my project, which is called Native Client, and then set that in the context of some of the other Google Client area projects to sort of give you a shape for the whole and how we think about these problems. Then I want to close briefly with a sort of a research agenda, some of the problems that I see as being the most best opportunities or most urgent in terms of ways to help with this. So let's talk a little bit about desktop systems and what's changed. Now, I think all of us, almost all of us, are old enough to remember Multics and the wonderful idea they had of 4 rings of security. Really, really interesting idea. The problem was nobody could figure out what to do with all those rings, right? And so by the time we got to the 70s, things looked kind of more like this. Unix and PDP-11 introduced a much simpler security architecture that just had kernel mode and user mode, and practically everybody knew what to do. Almost everybody. And this kind of system was reinforced by RISC microarchitecture in the 90s. So I thought we were done. I was in college back then. I thought, yeah, this seems about right. Let's get on with it. But then around 2000, a company called VMware resurrected the idea of the virtual machine, which obviously had a lot of traction earlier as well, companies like IBM. And okay, fine, whatever, we'll live with that. At the same time that this was happening, though, something even more disruptive was happening, and that was the web. Now, originally, I'm sure we all remember, the web was just a bunch of static web pages, HTML, you edit it with Emacs or VI, and you were done. Of course, then Web 2.0 happened. And so effectively, instead of the programs you wanted to execute being installed on your hard drive, now the programs you want to execute are coming from any place in the world. And here we are back to 4 rings. Isn't that amazing? I think that's really great. But recognize that the programs in this outer ring are totally different than what you've been thinking about in most of our careers. This code could be from anywhere. You don't know who wrote it. You don't know where it's been before it got to your desktop. It could be infested with all the worst possible things you could imagine. Of course, We all try to avoid those kinds of problems. But my point is that people expect to be able to switch to these programs with the same kind of abandon they change the channel on their television set. And yet there's some very dangerous things out there, and obviously our systems are not designed to deal with these kind of problems. So this I see as kind of an opportunity. I think there's some progress that's been made in some places, but there's a lot of places where we really haven't fully embraced and dealt with the problems presented by untrusted code. And this is one of the major changes I wanted to highlight. Next, I want to talk a little bit about, on a single machine, thinking about the structure of the actual operating system itself. Back in the 90s, people were pretty comfortable with a picture that maybe looked kind of something like this. You got an operating system kernel, which is really doing all the hard work. It's got the hardware abstraction layer, so you don't have to deal with devices directly. It's got resource management, like a file system and protection for files and accounts that you can log into. And then an application environment that gives applications a sort of stable place from which to, build from in terms of libraries and all of that sort of thing. So this was an incredibly useful model, and actually I think it's still pretty much the right model if you're looking at the data center. But when you look at desktops, I just don't think this model works anymore. The kind of thing I see on desktops nowadays looks a lot more like this. So yes, we still have an operating system kernel, and yes, people still do not want to write their own device drivers. At least most people don't want to write their own device drivers. But the resources actually aren't really on your system anymore. I think of my system these days as becoming a kind of disposable thing, like a cell phone. You don't really want state on your system. You want it in the cloud. That's the direction that things are going. And when resources are in the cloud, you can't really build the application environment into the operating system anymore. It's got to be up someplace higher, floating around in the cloud someplace. And so that's a part of why there's a lot of effort at Google going into open web platforms in HTML5 to establish a stronger open standard as far as application environments go. So this is a really huge change in terms of how desktop systems are used and the system infrastructure required to support those. And again, I don't really feel like we've recognized or addressed all of the problems involved in this really significant change. So those are the two problems I wanted to highlight. Next, we're going to talk a little bit about native client. And I'm just going to point out that it's a part of the application environment. Okay, native client is a project that I manage here at Google, and we're going to go into some detail now. The idea behind native client is to be able to run native code as a part of a web-based application. Now, some of you might be sitting there saying, native code, so what's the big deal? I mean, Microsoft and Netscape did that 15 years ago with ActiveX and NPAPI. Well, this audience, I probably don't need to advise, you probably shouldn't just run any ActiveX control that you happen to see or any NPAPI plugin that comes down. Some of them can be very dangerous. And the reason is that the NPAPI and ActiveX controls, they do more than just give you access to execute native code. They don't give you just access to the native CPU. They also give you direct access to the native operating system. And therein lies the problems, because through the operating system, you can have side effects like creating files or modifying files on your disk, like creating network connections to random places you never heard of and sending them spam. And it's that direct access to the operating system that's actually the source of virtually all the problems that we see with native code today. So the idea with native client is actually to give you full and direct access to the CPU, but no access to the native operating system. And that will allow us, we hope, to provide native code speed with the same level of safety that people expect from JavaScript and other kinds of web technologies we take for granted. So the way we pitch this is close the gap between the desktop and web applications. And that's really a high-level goal of all of our efforts in the client area. And a part of that gap that native client addresses is performance. We really want to be within small percentages of the best you can do on with a native desktop application. A choice of programming language is also very important. I always get frustrated with these systems that seem to assert you will only use such and such language. I think that's just silly. I mean, there's lots of languages, and there's a reason for that. They're all useful for different things. Related to that is leveraging legacy code. There's millions and millions of lines of open source C and C++, for example, that is very high quality code, but you can't really use in the web browser because you're just kind of stuck with JavaScript. So we want to solve all these problems, but at the same time, not sacrifice portability. The web is portable, right? You expect HTML to work anywhere, and that's critically important. That's an absolutely essential part of the web as we see it. and also safety, the obvious problem we've been dealing with all along. So well, that's why native code. Now, I wanted to give you a little bit more detail by what I mean by performance. And some of the key performance features of the system include, firstly, POSIX like thread support. If you look at where computer architecture is going, you're not really going to get much more performance through serial computation. It's all going to be through parallelism. And threads seems like, you know, the most direct abstraction for providing that. And this, by the way, is one of the key distinctions between the performance you can get from native client and a system like JavaScript, because the browser is very single-threaded. Another performance feature is straightforward access to vector instructions. I kind of see multi-core as one order of magnitude of performance looking forward, and vector instructions is another order of magnitude for code that actually does any sort of numerical or compute-intensive work. Vectorization is because of the boxed data types on JavaScript and also in Java, by the way, they really can't get any benefit from vector instructions. And lastly, hand-coded assembler. Now, it's never really that easy to write hand-coded assembler, but for the people who are ready to do it, we intend to not make it any more difficult than it already is. And this is actually very important to people who are working at the frontiers of performance, people doing things like video decoding, real-time animation, high performance, or, you know, sort of the latest game technology. They care very much about this sort of thing. So in summary, we want to deliver substantially all the performance, all the CPU performance of a desktop application, but make it in the browser as safe as JavaScript. So that's sort of the high level. What is he doing in this project? Now let's talk a little bit about the architecture of the system. And I'm going to explain that by running through an example, hypothetical web application that uses native client for some physical simulation. So maybe we're implementing a game, and someplace inside the source of the game, it's going to say, I want to use a native client module. It'll do that by either using an object or an embed tag, you know, in the HTML content. And this is the same way that Flash or ActiveX controls commonly get activated as well. So when the browser sees this, it looks at the MIME type of the file in question, and in this case, native client has been installed in the browser, and so we'll activate a container that is there to support the native client module. At the same time that it does that, the browser is actually also going to fetch the file that contains the content in question. Now, our physical simulation we're going to assume is safe, but for a moment, let's assume that, oops, you went to an evil website, and somebody was actually trying to play a trick on you and compromise your machine. Okay, the first thing that native client is going to do before it actually allows you to run this thing is run it through a static analyzer. It's going to disassemble the module very carefully and make sure that it's following a set of rules that we've created that we believe allow us to ensure that the behavior of the module is constrained and that it can't get this direct access to the operating system. In this case, it would look at this module and say, ooh, you know, bad stuff happening here, sharp edges, I don't like it, and say, I'm just not going to run it. On the other hand, for a physical simulation, let's assume that looks safe. So the static analyzer is going to say, this is fine, let's let it through. At that point, the browser will create the container for it and load it into memory. And it'll actually load it into a kind of a jail. We think of it as being like a jail, because there's a set of things that this module is simply not going to be allowed to do. So now that it's loaded into memory, we can start it running. We also establish a communications channel between the untrusted module and the browser. And at that point, it can do things like physics or animation or whatever kind of high-performance computing you need. So that at a high level is how our native client system is activated inside of a web application. Let's see. So a really fascinating and important aspect of this system is security. How is it that they think they can make this native code safe? And if you talk with people in the security community or binary analysis, you know, a long-standing problem is reliable disassembly of x86 code. And the existence of phenomena such as self-modifying code, overlapping instructions, these are all things that has made this problem very difficult. And it's sort of a key part of like the secret sauce, if you will, of the innovations that made this possible. So let's talk a little bit about this. What do I mean by safe when I say as safe as JavaScript? I mean no side effects except for explicit security interfaces, the system call like layer that native client provides. Now, what do I mean by a side effect? Well, here's one example. If you started your day by running this program, you might not have a very good day. It's going to try and remove all the files in your local file system. Clearly, native client modules should not be able to do this. If it was as simple as looking at the source code and seeing, the exec VE call, no problem. Unfortunately, things are quite a bit more complicated than this. There's a lot of variance to this kind of program. And here is an example as one of them. This program does exactly the same thing as the program you just looked at a minute ago, as long as you run it on Mac OS. But it does it in a sort of a sneakier way that I claim is pretty hard to discover. And to make the explanation a little bit more straightforward, I'm going to highlight a few key instructions. The first highlighted instruction is initializing an immediate variable with a 32-bit value. The 32-bit value looks just like some random number, but it's not. It turns out that the last 2 bytes are a system call instruction. The instruction, one of the instructions that native client will not allow you to execute directly. The next constant is computing the address of that same instruction, of that system call instruction, using the base address of the procedure. Now, clearly, this is very dependent on what compiler you've used to build this and all that. But, the people who are actually breaking into your systems, they have no problem with those kinds of challenges. And then the last highlighted statement is a jump instruction. It's actually going to use the address you initialized in that code address variable and jump to the system call instruction. The middle stuff is just setting up the stack so it looks to the operating system like a exec VE syscall. And voila, we've just blown away all your files. So this is a trickier example, and yet it's an example of a kind of program that native client has to make not possible. Okay, so another kind of threat that we're very concerned about is memory stores. Loads are also kind of interesting as well. And you just can't let this untrusted code have write access to arbitrary parts of your web browser or other places in memory that you might want to be protected. So native client is also, the sandbox that we use to run this untrusted code needs to be able to secure memory accesses as well. Now, a basic assumption in this system, and this is really driven by our portability goals, is that the operating system is not necessarily cooperative, and it's not necessarily bug-free. I mean, how many of you use a bug-free operating system, right? I don't think anybody was going to be able to raise their hand. This is a basic requirement for portability. So that's a threat model. Those are the kinds of bad things that we're trying to prevent. Now let me tell you a little bit about the system design and how we achieve these goals. The system is constructed with an inner sandbox and an outer sandbox. Now the outer sandbox is actually fairly conventional technology. You can read about it in a lot of papers, and there's references in the research paper on our website, so I'll just mention that in passing for now. The inner sandbox is a place where we've really done things creatively. And why there are 2 sandboxes? Well, we believe at Google and in my group in what's called a notion of defense in depth. Multiple layers of redundant defenses make a system quite a bit stronger than if you just hope that your single layer of defense actually works. So our inner sandbox is constructed using a technique called software fault isolation that was actually originally suggested by Wabi, Luco, Anderson, and Graham from UC Berkeley in the 90s. And it basically is using instrumentation before or possibly after key instructions to constrain their behavior in a way that has minimal impact on performance. We put that together with actually x86 segments. Remember segmented memory? I think most people probably saw this in their architecture class. x86, it turns out, has a wonderful mechanism that almost nobody uses to sort of reduce the amount of memory that you can look at. And so we rely on that very heavily, too. A wonderful thing about the inner sandbox is that to a first, it's just a little bit of a lie to say there's no OS dependencies. There's very minimal OS dependencies, and that makes it very portable. The same sandbox basically functions identically on all the operating systems we support, Windows, Mac, and Linux, and all of the NP API web browsers, including Opera and Safari. Because there's no OS dependencies, it's relatively immune to operating system defects. Now, the one caveat in terms of OS dependencies is a thing called LDT, local descriptor table initialization, which ironically it turns out is not supported on 64-bit Windows. And I don't have time to go into that in detail, but we talk about it quite a bit in the paper. And I'll just say we are, converging on a solution for that particular issue. Now, as I kind of alluded to before, we're going to actually change a set of instructions that the program is allowed to use. And because we prevent you from using certain instructions, we're going to need a modified compiler, a modified assembler, and a modified loader to follow all the rules that we're going to create to make this machine code safe. Fortunately, the modifications, we've been deliberately designing them to be very simple and open. And I'll describe some of the details in the next slide or two. But the part of the point I want to make is we really want to encourage other people to generate code for our system. We have no intention of having any sort of control or constraining effect on who can create native client modules. The last point about the Inner Sandbox, it has been very carefully designed to have very low runtime overhead, on the average of about 5% across Spec 2000 CPU. And I'll show you some details about that later in the talk. So, now how is this Inner Sandbox actually implemented? Let's look at some details. Firstly, I mentioned the problem of data and memory integrity. We don't want wild stores and writes and reads going on all over the place. And so the way that we do this is we use segmented memory on the x86. The green arrow indicates the data segment. That's going to be constrained by DS, ES, and SS segment registers. And by initializing those registers properly, you can actually prevent the thread in question from making any memory accesses outside of the constrained region. An attempt to make an access outside the region will cause an exception, and that in turn will cause the module to be terminated. So it's sort of a fail-safe kind of approach. Similarly, we constrain code to the area of the little blue arrow using the CS register. And this turns out is like incredibly fortunate. We get this level of really important protection for free just by using segmented memory. So, so that's one key part of the sandbox. And it takes care of our data references. Now, next I want to tell you about how we get control of control flow. How do we prevent an x86 program from branching into the middle of an instruction, like that 6-byte instruction that was used to initialize the immediate variable in the previous example? And the answer is we have a set of rules that we use to make x86 disassembly reliable. I'll go through these briefly. First, all valid instruction boundaries are determined by a top-to-bottom disassembly of the text. In other words, we just disassemble from top to bottom, and the instructions we see defines the instructions you're allowed to use. And any instructions we didn't happen to see, we're going to prevent you from using those. A second rule is that all aligned addresses, and we use 32-byte alignment in most of the time in the system, must be a valid instruction boundary. In other words, if an instruction crosses a 32-byte boundary, we will not let you run that piece of code. Computed jumps use sandboxing to force alignment. If you're jumping through a register, or in any case in an address we cannot understand statically, then we're going to use a masking instruction before the jump to make sure that the address jumps to an aligned boundary. Now, since in the previous rule we've checked that instructions never cross an aligned boundary, we know that the target of a computed jump must go to an instruction that we've already inspected. Okay, and this is a key part of the reliable disassembly. Branch targets have to be within the code segment. We get that for free from segments. And we don't allow mixed text or data. You can't have arbitrary data in the code. We don't allow overlapping instructions or dynamic code generation. Those are just, sorry, you can't do those anymore. You had to give up something, right? So let me tell you a little bit more about what the masking sequence looks like for a computed jump. Now, normally people look at x86 machine code. You might see a call instruction like this. It's going to a known address. In that case of that first call instruction, we know exactly where it's going. We can statically check that that's an instruction we saw during our top-to-bottom disassembly, and if so, then we can make sure that it's safe. The second call is a little bit more problematic because it's using an address that can only be known at runtime. So to make sure that's safe, we're going to use a pseudo instruction, NACL call, And that will be expanded by the assembler into the 3 instruction sequence that follows that masks off the bottom bits of the address before doing the control flow transfer. So that way, we know that you're only going to go to an aligned address. And remember, we checked all the aligned address before to make sure that they're safe. So this is our strategy for making sure that you can never branch into the middle of an instruction or otherwise go to an instruction that we haven't already inspected. And that's the reason why we can, given this as a tool, as reliable disassembly, we can actually exert some power over the binary and prevent you. We can actually remove instructions from the instruction set, and this is where it kind of gets fun. So, so this next slide describes some of the restrictions, some of the additional restrictions that we're going to put on native client modules. Firstly, we're going to leave out some instructions. Now, I already mentioned syscall. It turns out int is also problematic because I think there's a way to do a syscall with an int instruction. Furthermore, we're going to prevent people from using the return instruction. Now, this one kind of confuses people sometimes. I mean, how are you going to do a procedure call if you can't return? Well, don't worry. Actually, you can just replace the return with a pop and a jump, and it does the same thing. But the weird question is, well, why can't you use the return instruction? And the answer is, like I mentioned earlier, we're really committed to first-class thread support. And if you check the return address on the stack and then jump to it, you could have an evil thread someplace else that was trying to construct a little race where it changed the address between when you checked it and when you jumped to it. So for threaded programming, that wouldn't work. By doing a pop and then a jump, you actually have the address in state that's specific to the thread. It's in a register, so no other threads can see it, and that makes the check safe. In addition to omitting some instructions, we're also going to restrict prefix usage, and I won't go into this too much, but people who know x86 assembler know there's a lot of prefixes. Some of them do very strange things. Some of them just don't make sense sometimes. And so we're really going to clamp down on that and only allow prefixes that make sense, and at most 1 prefix per instruction. Now, mind you, I'm talking about 32-bit x86 code. For 64-bit, we're going to have to bend these rules a little bit, but we're still going to have the same relatively strict policies. Another interesting aspect of this, we really are aggressive about wanting people to be able to use instruction set extensions like SSE3 and MMX and all the other wacky, wonderful new stuff that AMD and Intel are continuously trying to provide us with. There's a problem, though. Imagine that you have a piece of code with an SSE42A instruction, and you happen to have a machine that only has SSE2. Your SSE2 machine is not going to know how to decode that SSE4 instruction. And if we let you just go and try and execute it, you might get the instruction length wrong. It might behave in an unpredictable way, and that could possibly be an exploitable defect. So what we're going to have to do is when we're disassembling and analyzing the binary, we're going to use the CPU ID information from the processor to recognize exactly which instructions are not supported by the CPU in your machine. And when we see an instruction, like the SSE4 instruction on an SSE2 machine, that shouldn't be executed, we're going to override it with halt instructions, such that if the program ever actually tried to execute that instruction, it would halt, but it would not cause any damage. And that's sort of an example of a kind of a general philosophy in the system that we can't force developers to write correct code. We can't force them not to write buggy code, but we can constrain their code to a certain set of safe, constrain the behavior to be more safe. Question, yes? Actually, Ron is coming with a microphone, yes.
All right. But I never thought I would see a day when somebody would love segments that much.
Yes,
the question I had, though, is that you have a whole bunch of restrictions to Sandbox. But then, Intel did have rings, 0 to 4. And then you have platform evolution, where you have on the platform things like TPMs. And you didn't consider using any of those hardware assists to actually sandbox you, or is it really, because as you pointed out, ISA extensions are very common and they will keep happening.
Yeah.
And so you're in a race.
The high-level answer to that question is that one of the highest priorities in the project is portability, and a lot of the cool features that might make this easier on certain operating systems or certain hardware simply do not allow you to create a portable system. So the rings in the Intel microarchitecture, for example, it's kind of the right idea, except you can still use the system call instruction in the outer ring. We've actually, I would like to see a new ring or modifications to the existing ring where you could actually remove instructions from the instruction set. If you gave me a microprocessor that did that, I could significantly simplify.
And you don't think the VTX extensions in the inner ring help you in that?
They don't have what we need yet, no.
Okay.
So
Thanks.
let me plow through the rest of this. We are a little bit time pressured, and then there should be plenty of time for questions at the end, though. So if any of you are paying attention, then you probably are worrying about security. Like, geez, this sounds like pretty cool research, but you really want me to use this on my laptop? I don't think so. Well, what I wanted to try and assure you of is that we're really worried about security too, and we're doing everything that we can possibly think of, and in all cases applying best practices to try and make this thing as secure as we possibly can. So some examples of some of the kinds of steps we've taken. We do multiple internal security reviews, and this is not just for native client or client projects. This is for anything that gets released and is customer-facing in Google. There's a design review and an implementation review. We have very smart people who are really good at breaking software, and so we've been through that several times. We've open sourced our system because we strongly believe that public review and public scrutiny will make the code better. Towards that end, we've also published a paper in IEEE Symposium on Security and Privacy this year. And we held a security contest. And that was really fun, actually. The security contest, we put money on the line, $8,192, to the person or team who found the most bugs. And some interesting statistics about the contest. There were about 400 teams that registered, about 600 individuals, and among them there were 22 bugs reported. So that means there were probably a lot of frustrated people out there. The bugs that we saw were actually very, very good. Some of them were, complete exploits that, totally destroyed the system. But they were also almost entirely implementation defects. We didn't see anything that was a fundamental issue with the architecture. And almost all the issues we saw were things that we could fix in a couple of days. And I'm just really pleased that we found them before we put this on, 10 million desktops, right? So, so the security contest was great. We're not done with that either. We've got more security reviews planned and new kinds of testing before we would expose this to end users. But this is the kind of scrutiny that I think a technology like this needs in order to approach the level of safety that that is, we feel is our obligation before we would put this on a large number of desktops. So that's what I wanted to tell you about native client implementation security. Let me tell you a little bit about what we've done with the system now. We ported a bunch of stuff, mostly demo type code, but some of it is, non-trivial. Quake 2, for example, the computer game from the 90s, which some of us wasted a lot of time on, runs really nicely in native client. We've ported video decoders. We ported a lot of big Linux libraries just to see how it would go. And then we've implemented some applications on our own as well. And I'm going to demonstrate one of those in a minute. I mentioned something about performance earlier. I wanted to show you the numbers. Native client, on average, tends to have about a 5% performance impact. And the average number is the red bar all the way to the right. Now, sometimes we have a larger performance impact. For 32-bit alignment, it can be as much as 20%. And the reason for that is generally instruction cache pressure. Because of the alignment rules and because we change some of the instructions and add instructions, we can actually increase the text size up to 50% in some cases. Fortunately, most programs have a working set size that's much smaller than the huge caches on modern machines, and so it usually doesn't matter at all. But if you have a program like some of the unusual code you find in Spec 2000 that's right at the border of where the instruction cache kind of ends, then you can run into sort of unusual behavior. Other cases, we actually make the code faster, and that we thought was really kind of strange and irritating at first. It turns out that our alignment has a very positive interaction with branch prediction and keeping cache lines full and that sort of thing. So because we're aligning all of these instructions that weren't aligned before, we sometimes make code actually run faster. And actually, that's not just a random weirdness in spec. We actually see for kind of typical code that we work with, plus or minus 3% is sort of what we expect in terms of how we'll impact performance. So next, I wanted to show you a little demo. Let me see if I can actually, this might be tricky. Okay. I wanted to show you a little demo of a program running in native client, give you a feel for where it's actually at these days. And this is also representative of one mode of usage that we think is going to be common. This is called Native Client Darkroom, and it was really inspired by Adobe Lightroom as a place to work on, make modifications to photographs. So over here we've got a bunch of controls. All of these controls and the whole user interface actually was implemented in JavaScript using fairly ordinary, straightforward methods. But this area here is controlled by the native client module, and it's going to be doing the image processing. So I'm going to load an image into the module. I haven't really done anything impressive yet, right? I mean, you can certainly do this in a web browser today. But the place where it gets interesting is when I start using these modifications. Now, if I did image processing in JavaScript, we would be talking about seconds per frame, right? It would probably take 15 seconds to do anything to this image. But with the native client module, I can actually do these kinds of updates, like changing the geometry of the image in real time. We're seeing about 15 to 30 frames per second here. What you get will depend on the CPU in your system. But the point is, don't try this in JavaScript because it just won't be much fun. So this is sort of making the point that if you give real live CPU speed for web-based applications, you can enable things that people might not have imagined possible. So with that, let me get back and finish off the rest of the talk. Okay, that was the native client darkroom. So there's a lot of related work in this area. Sandboxing work, like I mentioned, started in the 90s with Wabi, Luco, Anderson, and Graham. I don't have time to go through all of this right now, but it's covered in quite a bit of detail in our research paper, and I really encourage people to have a look at that. It talks about a lot of what we're doing in more detail. Now, we started earlier in the talk talking about desktop OS structure, and I wanted to give you a little bit of a notion of how this project fits into other desktop projects at Google. So, like I mentioned, native client is something we would like eventually to become a part of the application environment that's available to web application developers. I wanted to mention some other Google projects that also fit into this space. So if you think about the application environment, it's really built around HTML5, open standards for web applications. And they're becoming more and more powerful each day. And there's a lot of things that they do extremely well. We're very, very supportive of that. One thing that they don't do is high compute performance. And so for that, we have native client to provide direct access to the native CPU. Another thing that they don't really do very well right now is hardware accelerated graphics. And that's what the O3D project is for. Now, all of these live inside the Chromium web browser or Firefox or Mozilla or whatever other browser you might want to use. And over time, we want to move all of these things towards being web standards. Today, they're probably best supported in Chromium. And the browser is also becoming the important thing that takes care of this resource management. It actually has the infrastructure you need to manage resources that reside in the cloud. Then on top of that, we have a hardware abstraction layer, and you could use a full-blown operating system for that. But the full-blown, Linux or Windows actually has a lot more stuff than what you actually need to run this environment properly. And so that's sort of some of the motivation behind Google Chrome OS, a much simpler foundation for building this kind of web-based application stack. Some of you are probably sitting there thinking, okay, so he told me about the problems, and then he told me how Google's solving all of them. Thanks a lot. Have a nice day. That's not really the message I want to deliver. And the fact is, yes, I think our projects are interesting and ambitious, but there's also a sense in which I think we're really just kind of addressing some of the stuff that we should have been doing in the 90s. And looking forward, I think there's some much more difficult and equally interesting challenges. So I just wanted to spend a few minutes talking about those. Internet security. Is it really impossible to design software to be safe? few people will argue with me about the notion that the web today is a cesspool. And I'm not really even talking about offensive content. I'm talking about crime, spam, botnets, phishing, fraud, in short. And the status quo is the result of an accumulation of things that have come together over these systems incrementally patched over the last 10 or 20 years. I don't really see a fundamental reason why the world needs to be this way. I think what we're lacking is a principled foundation for secure systems that run internet-based applications. And there is research out there that gives me hope. For example, the HiStar work by Mazieras and Zeldovich, I think, is making a lot of progress that not only applies the principal foundation from information flow control, but also makes tremendous improvements in the usability of that kind of technology, which was really the big problem in the past. So I don't think this problem is something that can be neglected, and indeed I think it's really timely. And when I think about other kinds of contexts, for example, designing a wall surface that is resistant to graffiti, or designing an airport entryway that can be secured, I don't really buy it that things are harder in software. I think it's just there are other constraints that make it very challenging. Some of them are technical, some of them are non-technical. But the technical part of it, I don't think that it's that much harder than problems in these other contexts. I just think that we need to draw our attention back to this area and think about it a little bit harder. Another area that I think is really interesting is power. And so this challenge I think of as being really wireless computing. Get rid of the power cords. Now you might be thinking, Brad, he's totally nuts. I mean, what is he talking about? What can you possibly do without power? Well, I brought a couple of props that Brian Bershad's group sent me from Seattle. These devices are called a Radish, and they actually you'll see them outside the conference rooms in this building. This is the device that runs totally on solar power. It has a 1 megahertz processor, and right now this one is only useful for showing CAD images, and this one I think I broke it. So so you're not going to be able to get much of a demo out of these things. But the point is that it's not absurd to think about computing based on ambient light. There's actually, an existence proof that you can do something that's not exactly trivial. And so I think the interesting challenge is pushing forward on that and pushing the envelope on what you can do with ambient light. I'm going to pass these around and then talk a little bit more. And these are obviously not the only devices that would fit in this space. There's, there's interesting cell phones that are solar charged and that sort of thing. So if you think about what are the technical challenges to doing this, I actually come down to 3 words, all of which begin with P: power, performance, and parallelism. In terms of power, it's kind of neat to hear people talk about laptops that can run for 8 hours. But personally, I think that's a crock. I think we need to be much more ambitious than that. Now, to get better power, certainly there's some hardware work to be done, but I think there's actually a lot of software work to be done as well, because the inverse of power is directly related to performance. And if you're going to work on the performance problem, then the perspective that I think is useful is think about the fact that over the last 30 years, all of our behavior has been conditioned by a world where CPU speed doubled every 2 years, right? Well, we're done with that. That's not really going to be the way things are right now. And if you think about that assumption and all of the implications it's had for how we build software, I think that provides some vision, some notion of how you can actually start to think about software that computes interesting things on extremely low power devices. The third P is parallelism. And a lot of people in the audience I know are already doing wonderful work in this area. I think of Louis Ceze's work and Sasha Fedorova, and there's a lot of really great work going on in this area. But the fact is that it's the only way you're going to get substantially more computing performance without totally rupturing the power envelope. So I think of this as being a really interesting challenge, and I would be delighted to see research progress that actually pushes the envelope in terms of what you can compute with ambient light. The last challenge I wanted to suggest is reliable software. What would it take to make software really reliable? Now, I really like the work by people like Dawson Engler, and Lewis has done some of this as well, where you analyze programs to check for what kind of bugs they have. The thing that's a little frustrating about that is sometimes it reminds me of my experience owning a car in the 80s, where the industry response to a broken automobile was a worldwide fleet of service facilities. Not make the car better, just like extract more money for service. I really don't think, I mean, obviously it didn't work terribly well for the auto industry ultimately, and I don't think it's the right approach to take with software either. I think that we can do better than that. I'm actually, so there's obviously a lot of interesting work going on already. And one of the things that I saw most recently that really gave me hope in this space is an article published in the most recent Communications of the ACM by Xavier Leroy from INRIA, Roconcourt. He actually discusses a C compiler that he has not just implemented, but also proven correct. That's a really complicated piece of software. And if you can prove a C compiler correct, then I think that there's more that we can do for other kinds of programs as well. So that's my soapbox. That's the end of my talk, and I'd be happy to take questions on any of the things we talked about today. Also, I saw Matt Papakipos here a minute ago. Oh, maybe he left. Okay, I apologize that. I do want to mention Matt Papakipos. He was instrumental in starting the Chrome OS project as well as O3D and Native Client, and he's really responsible for a lot of the vision that's driving many of the things I talked about. So I'd be happy to take questions.
Hi there, Brad. So right at the end of your talk, you said somebody had proven a C compiler correct. Have you taken any stabs at proving your Sandbox correct? Do you think that that's feasible? And attached to that, would it be easier if you could say convince Intel to make a small change or two to their hardware to enable the kind of security they're doing instead of doing all of this work in software?
That's a great question. I have thought about trying to prove our system correct. I've even thought about asking other people to do it as a research project. It's obviously a very hard problem. I did have a conversation with Dawson Engler about this once, and you know, the kinds of, let's see, I have to think a little bit about why it was that was a difficult problem. But you have to be able to state what the expected behavior of the system is, and so it's something that we'd like to work on. It is perceived as more of a research problem than a product problem, so it's not the easiest thing in the world for me to get staffed. But I am, you know, eager for collaborators if people are interested in that. And by the way, one of the coolest things about working on client software at Google is it's almost all open source. And part of the reason for that is because we want to encourage collaboration and independent innovation. And I think that's part of the reason why I'm really happy to be able to talk to people about it this morning. Now, the other part of your question was talking to people like Intel, for example. There are definitely things that they could do, and we're definitely going to talk with all of the interesting CPU vendors that we can have a conversation with. And indeed, we're talking with a bunch of people already. Keeping that in mind, you know, Google usually thinks in time frames of about like 3 to 6 months, and Intel thinks in time frames of like 5 years. So no matter even if they did everything we asked for, we would still have to do everything that we're planning anyways. So don't imagine you're going to get any quick fix from that kind of company. But there are huge opportunities, and I think some of them are relatively obvious, and some of them are actually like interesting research. So yeah. Other questions? Kim.
Okay, so I had a question about Native Client. It's a really cool project. One of the natural critiques that you're obviously going to run into is that everybody has to recompile all of their software. Some people don't have the source anymore. There's legacy binaries that are around. So have you thought about, and are you exploring the notion of binary translation, dynamic optimization to do some of the things that you want to do on the fly?
Yeah, that's a very interesting topic, actually. Some of the best translation systems right now are kind of dynamic, and that's a handicap for us right now. Right now, our system requires that it can statically analyze all the code before we run anything. But we are thinking about if there's ways that we can loosen that. And even if you continue to have the static analysis requirement, there is a lot of code out there that we think could be analyzed and translated effectively. One of the neat things about the project, former systems that attempted doing binary translation were often designed to run on the desktop. And that's actually like the hardest place to solve this problem because the desktop user obviously is not going to know what to do if things don't work. With native client, if we had a translator, it should be possible actually for the developer to run all the tests that they have available before they ship the software. And if something isn't quite working, they can, maybe go back and tell the translator how to improve things. So, so you won't find any binary translation work in the source code base, and it's something that we're thinking about using in some scenarios. Although I can tell you honestly, we're not working on it yet, but we are hiring all the best compiler engineers we can find. And so feel free to send me students. Yeah, it's a very interesting, and it's also, like I said. The compilation, we don't want to have corner the market on compilers for this thing. We'd be thrilled for other people to be generating code for our system as well. So, other questions?
In the interest of time, we need to make this one.
Sure. Yeah, this can be the last question.
Oh, I was about to say I have 2 questions. So once upon a time, x86 is only one of the native environments. So do you see your system? Actually, I can certainly imagine desktop disappearing into palm tops, and probably x86 may not be the only choice. And how much is this really neat solution? You give this such a convincing demo. How much of that is tied to x86 specifically?
Yeah, well, your question is a good one, and it's actually one of the reasons why inside the team we have a little motto of full employment for compiler engineers. But we have stated publicly that we're working very hard on an ARM port. We also need to support x86, a 64-bit version. That is an x86 environment without segment registers. That is only a part of the solution to achieving the level of portability that people expect from the web. And the rest is kind of like research, actually. If you start thinking about instruction set neutral distribution formats for high performance code, and keep in mind that we're really not willing to sacrifice anything in terms of performance, then you're definitely outside of the range of like common practice and into some of the kind of the scary, edgy kinds of technologies. So we should probably let you take your break. I've already burned through most of it. I apologize about that. But I will be here pretty much all day today, and I'd be delighted to talk with people more about these projects. Thank you.
Thank you.